Shear force and bending moment. Shear force and bending moment are internal forces that result from the effects of external forces. The design of any structural member requires finding the force acting within the member to make sure the material can resist the external loads. If you make a cut at any point on the beam, the internal forces are normal force acting perpendicular to the section, shear force acting along the surface, and the bending moment. The forces on the left and right sides of the section at C are equal in magnitude, but opposite in direction. When the two sides are reconnected, the net force is 0 at the section. Although choice of sign convention is arbitrary, these are the sign conventions often used by engineers. Steps for drawing shear force and bending moment diagrams. First, we draw an overall free body diagram. Then, we write down the equations of equilibrium and solve for the support reactions. Next, we take imaginary cuts along the beam and draw a free body diagram for the sections, showing the normal force, shear force, bending moment, and external forces. By applying the equation of equilibriums, we can solve for the unknown internal loads and write down their functions. Last, using those functions, we graph the shear force and bending moment diagrams. Here is an example. The question asks us to draw the shear force and bending moment diagrams for the loaded beam and determine the maximum value of the moment. The first thing we have to do is to draw a free body diagram for the entire beam to solve for the unknown support reactions at A and B. Notice that since the sum of forces in the x direction equals to 0, therefore the horizontal component of support A is equal to 0, and we only include the vertical force Ra on the free body diagram. We then apply equations of equilibrium. By taking the sum of moments at A equals to 0, and the sum of forces in the right direction equals to 0, we found that Rb and Ra are both equal to 4 kilonewtons. So the next thing we want to do is to section the member. By looking at the different loadings on the beam, we can decide where we want to cut. We take an imaginary cut at x equals to 2 meters and draw the free body diagram for the right hand side. Notice that in this section, we're using the sign convention with a negative shear force and a positive bending moment. In this case, if we make a section cut from the other side of the beam, the resulting shear force and bending moment will be the same in magnitude with this section, but with an opposite sign. Using equilibrium equation, we can solve for V and M. Moving along the beam, we make another cut at x equals 4 meters. In this section, we have a distributed loading with the intensity of 4 kilonewtons per meter. Therefore, we have to replace it by a concentrated loading first. The magnitude of this concentrated force is the distance of the distributed loading across the beam times it by its intensity, which is 4 times x minus 2, and it is located at the central location of the distributed load, which is half of x minus 2. And now we can apply the equilibrium equations and solve for V and M. We found that shear force function is V equals 12 minus 4x kilonewtons, and the bending moment function is M equals negative 2x squared plus 12x minus 8 kilonewtons meter. Now that we have shear force and bending moment functions, we can now graph the shear force and bending moment diagrams. Notice that the maximum bending moment occurs at x equals 3 meters, where the shear force is 0, and the bending moment is 10 kilonewtons meter. Here are some things about shear force diagram and bending moment diagram that will be useful to be remembered. When a concentrated load is acting on the beam, the shear force diagram consists of horizontal lines with vertical jumps at the points where the force is acting. On the other hand, the bending moment diagram consists of sloping straight lines which changes direction at the point of application. When a uniformly distributed load is acted on the beam, the shear force diagram consists of sloping straight lines, and the bending moment diagram consists of parabolic curves. At pin or hinge joint, the bending moment is always zero. Here are some shear force and bending moment diagrams under different types of loadings. Thank you for watching.